How was the solar system formed? Have you ever lain in bed, staring at your window at the night sky in clear weather? Perhaps, while doing so, you were struck with the realization that no matter how beautiful the stars look, you actually have no idea how they got there. And not just the stars, but also the sun, the moon, even the very Earth you're lying on right now too. If you can relate to this, you're definitely not alone. The formation of our world has been a mystery that has fascinated many astronomers and scientists alike for generations. It's a topic that's considered crucial for humanity to understand, as it unveils the origin of Earth, our home, and the many neighbors surrounding it. Today, we're going to unravel this very mystery as we take a deep dive into the origin story of our solar system. So for all those wondering how the solar system was formed, stick around to find out, because the entire process is more spectacular than anything you can think of. Birth of the Sun. All celestial bodies in our universe share a common origin, the Big Bang, about 13.5 billion years ago. The first stars that came as a result of that expansion lived out their lives, and eventually died in a massive explosion, giving birth to a new generation of stars. These new stars also lived out their lives, ending with their own cosmic explosions that send out the materials for future stars to thrive. Our Sun is considered one of these future stars, falling within the third generation. In fact, our entire solar system is made of the recycled material of previous star generations. The story of our solar system starts about 4.6 billion years ago, during this third generation of stars, within a large concentration of interstellar dust and hydrogen gas. These regions are called molecular clouds, and they span light years across space. Gravity, the driving force behind most of the solar system's formation, helps shape this large cloud into something much greater. You see, as our molecular cloud becomes gravitationally imbalanced, accumulating mass in the form of gas and dust, a massive transformation took place in the very center of the cloud, the formation of a protostar, a celestial body still in its infancy that one day would go on to become the sun that lights our skies today. The massive gravitational pull of this protostar drew in even more gas and dust, accumulating more mass and energy. The temperature and pressure in the core of the protostar eventually skyrocketed, culminating in the pivotal moment, the ignition of nuclear fusion. This is where the true star came to life and got to work, with the fusion of hydrogen atoms dispelling massive amounts of light and heat energy. The newly formed star soon entered a phase known as the main sequence, a delicate balance between the outwards pressure from the nuclear fusion and the inwards pull from the massive gravity. This equilibrium has kept the star illuminating the cosmos for billions of years to come. The building blocks of planets. As the Sun was newly formed, the leftover material from the molecular cloud formed a swirling disk around it called the protoplanetary disk, which over the course of countless millennia served as the forming grounds for all the planets of the solar system. Composed of elements like carbon, silicon, and oxygen, along with ices of water, methane, and ammonia, the protoplanetary disk is a treasure trove of potential worlds, holding the key to the formation of planets, asteroids, and comets. Within this disk, the forces of gravity worked their magic in intricate ways. Tiny particles, often no larger than grains of sand, came together and stuck to each other, bound by each other's mutual gravitational pull, to form larger and greater cosmic bodies. This process is known as accretion. Over a long period of time, the continued accretion caused these bodies to morph into structures called planetesimals. These are the building blocks of planets, ranging from just a few meters to hundreds of kilometers in diameter. The inner regions of the protoplanetary disk, that were closer to the Sun, were too warm for volatile substances like water and ammonia. Solar wind from the Sun also pushed volatile particles outwards and away from the inner regions. What remained were mainly dense materials like rock and metal, which in turn gave rise to rocky planetesimals, laying the foundation for the terrestrial planets of the solar system. Meanwhile, in the colder outer regions of the disk, beyond an imaginary boundary that has been called the frost line, more volatile materials like water ice, other ices, and gases prevailed. This led to a different set of planetesimals taking shape, providing the raw materials for the future gas giants. Another really interesting fact to note here is why planets are always spherical in shape. The answer to that, once again, lies with gravity. You see, during accretion, when planetesimals form and use their gravity to attract more objects and grow further in size, that gravity pulls in materials equally from all sides, like the spokes of a bicycle wheel. And what structure in 3 dimensions do we know of that is equidistant from the origin on all sides? That's right, a sphere. Of course, not all planets are perfectly round because of factors like the equatorial bulge, but they're all approximately spherical. Formation of the terrestrial planets. As the cosmic process of accretion continued over an extended period of time, the inner regions of the protoplanetary disk witnessed a large transformation. Closer to the heat of the young sun, rocky planetesimals took center stage. As they grew more and more substantial, their gravity was enough to influence the motion of each other. Under this gravity, the planetesimals collided and amalgamated, slowly but surely building up to the foundations of the terrestrial planets. Through a process known as differentiation, these protoplanets developed distinct layers, with dense metals sinking to their cores and lighter materials rising to form their mantles and crusts. This process continued within the inner regions of the disk until only 4 large celestial bodies remained: Mercury, Venus, Earth, and Mars. The terrestrial planets had arrived. Shortly after Earth formed, so did the Moon. A large celestial object, about half as wide as Earth, collided with our world, giving off a massive amount of energy. This energy not only disintegrated the colliding object, but also melted the Earth's outermost layers, flinging debris out into orbit. These materials, forming a ring of gas, dust, and molten rock around Earth, eventually underwent their own process of accretion, growing larger and larger to eventually form our Moon. Formation of the gas giants. Beyond the warm regions of the inner disk, past the frost line, lies a much colder realm where ices have been dominating. Here, the story of planetary formation was a bit different. They began as solid cores formed due to the accretion of planetesimals, similar to their rocky counterparts. But their immense gravitational pull, combined with all the gas that exists in this region, essentially turned these growing planets into massive celestial sponges, making them absorb the surrounding gas in large volumes. This process skyrocketed these planets to their massive size. For perspective, imagine inflating a balloon with gas until it becomes really big. That's essentially what happened here. This is also where these planets get the term gas giants from. Each gas giant was different from the next. Jupiter was known for its wild storms and powerful magnetic field. Saturn stood out from the rest for its famous layers of rings, making it a cosmic beauty. Uranus and Neptune, termed the ice giants, harbor a fair bit of mysteries under their chilly atmospheres, and there are questions about their formation that the scientific community is still in the process of finding answers to. Late heavy bombardment and stabilization. The early years of the solar system were a tumultuous period where Earth and the entire inner solar system underwent an intense spike in asteroid bombardment roughly 4 billion years ago. The theory behind this event is known as the late heavy bombardment theory, and it has shaped our understanding of the early evolution of the Earth. Some of the asteroid impacts from this period were massive, leaving lasting impacts on the surfaces of the planets. This is also where the Moon's craters are said to have originated from. As violent a time as this was, it came to an end eventually. Things calmed down. The solar system settled into the familiar arrangement that we see today, with planets finding their orbits. The solar system had finally stabilized. So, there's the answer to your question. The formation of the solar system is a story of order emerging from chaos, from a primordial cloud of scattered molecules to the organized, rigid solar system that we live in today. Hope you learned something from this video. Thanks for watching.